Okay, good afternoon, everyone, or good morning, depending where you are in the world, and welcome. Today, Jason and I are here representing Mars Petcare, and today we'll be discussing how we leveraged Apache Spark and Delta Lake for efficient data encryption at scale. So I'm just going to take you through the agenda today. So first, I'm going to start off with a bit of background about the authors, Mars as a company, and the Petcare Data Platform, which is the foundation on what our team here has built. And then I'm going to talk you through a bit about CCPA, because this was the main motivation for the project, and how this has enhanced consumer privacy rights and consumer data protection. And then finally, the main bulk of this project is going to be around Gecko, and this is going to be a deep dive into our bespoke automated CCPA compliance tool. And within this section, we'll be discussing the encryption and how we've utilized Spark and Delta Lake in order to make this possible on a large scale. So background first. So there were two authors for this particular project. So my name's Daniel Harrington. I graduated last year from the University of Bath with a master's in integrated mechanical and electrical engineering. I've since transferred to become a data engineer here at Mars Petcare. I've been working here for around 10 months now. And in my time here, I've worked solely on Gecko, which is the bespoke encryption layer that we've designed here in the engineering team.
And hi, I'm Jason. I graduated 2 years ago with a Master's in Physics from the University of Exeter. And I've been a data engineer here at Mars Petcare now for about 16 months. And in my time here, I've kind of been split between two different projects. So the first 8 months that I've been here, I've worked on the design and implementation of our ELT framework. And in the latter 8 months, I've been working on Gecko with Dan. So just to begin with a bit of an overview on Mars Petcare as a company. So Mars are a broad range and a diverse family of a broad range of companies that are constantly evolving, ranging from confectionery products and food to pet care as well. So moving into Mars Petcare, Mars Petcare began with the pet nutrition brand called Chappie and has since expanded to a broad range of businesses spanning multiple different sectors within pet care. So some of the areas that these businesses work in include pet nutrition, for example, Whiskers and IAMS and Chappie, as well as pet health or pet hospitals, for example, Banfield and VCA, and also tech products, for example, Whistle, which is kind of like a Fitbit for dogs. So now moving away from Mars and looking more into the Petcare Data Platform and the team that we work in, the Petcare Data Platform is the team that basically manages a platform of anonymized data from lots of these different businesses from within Mars Petcare. So the kind of foundation of this platform is Kite, which is our ingestion framework and our ELT pipeline. And this is the pipeline which connects to multiple different business units from within Mars Petcare and standardizes that data into a final output. So you can imagine that a lot of these different business units have a lot of different systems that we're pulling data from, for example, whether that's a Postgres database, SQL Server, or Azure Blob, for example. And we bring this all in and standardize it into a single output. We've then built engines and design processes on top of this output in order to enhance the business value and integrity of the Petcare Data Platform. One of these being Gecko, which is our CCPA compliance ecosystem designed for Spark and Delta Lake. So if we have a brief look at the architecture diagram of some of the things that the Petcare Data Platform do. So if we look here on the left, we've got Kite, which is our ingestion framework. And this is really where we bring in everything from the multiple different sources into an output ready for use for the other engineers and the analysts within our team. We then have transformations on top of this output, Gecko being one of them, which we're going to be talking about for the rest of this presentation. But we also have a framework for dynamic transformations, which is driven by JSON configs. Then on top of these transformations and this transformed data, we have what we call engines, which are essentially data lake houses or data models, which are built on top of these transformed data sets in order to add business value for analysts and external teams as well. We then also have a bit of marketing and activation work, as well as web services, which we use within the engineering team to help things like monitor and trigger runs.
Okay, so I'm now going to give you a bit of background around CCPA and how this affected the design of our project. So CCPA, for those that don't know, is the California Consumer Privacy Act, and this has been effective from January 2020. And it's the first law of its kind in the US. and it gives users more rights surrounding the data that they share with businesses and how this data is stored, used, and shared. So there are three key rights that come with CCPA. The first of these is the right to opt out. So this gives users the right to opt out of having their data sold to third parties. The second of these is the right to request disclosure. So a business has to disclose all of the data that they have around a consumer. And thirdly, and most importantly for this project, is the right to request deletion, or the right to be forgotten. And this gives users the right to have all of their personal data removed from the systems of a business. So whilst this sounds simple in concept, our old process that we used in order to become CCPA compliant was actually quite complex, because we had to find every instance of an ID in our data lake and physically delete the row. In a data lake as large, as complex as ours, this process was very difficult to manage and required a lot of manual work for us to become CCPA compliant. In order to improve on this process, we came up with a three-part mission, which formed the basis of Gecko. The first of these parts was to handle CCPA right to forget requests efficiently, safely, and effectively. As there can be many dependencies between different data sets in our lake, and people may occur in any number of different locations, we wanted to ensure that we designed a consistent, reproducible, and tractable method to ensure that requests could be filled with confidence and in a quick and efficient manner. We also wanted to make this process as simple as possible for audit purposes, where we can clearly show what steps have been carried out in order to fulfill a right to forget request. The second part of our mission was to increase the overall security of PII data in the Petcare Data Platform vault, as this is a very important aspect of what we do here in the engineering team. And thirdly, we wanted to maintain the non-PII data structure in order to continue to provide analytical value and data integrity. PII forms the basis of some really interesting and valuable projects within our team, so it was a key aim to ensure that this PII that we are allowed to use is still available for use by our analysts. So how did we achieve these goals? Well, I'm now going to talk to you a bit about the Gecko ecosystem, and I'm going to explain some of the core concepts behind this. At its heart, the Gecko ecosystem is our bespoke automated CCPA compliance tool. And the key concept behind it is that we utilize row-level encryption for PII data and store these encryption keys in a single Delta lake in our table. Gecko is made up of two core functions, these being the Gecko crawl and Gecko delete process. Gecko crawl is what handles the encryption and decryption of our PII data, and we also generate a master table which contains all PII within the Petcare Data Platform. The crawl process was also the namesake for our project. A quick Google search of animals that crawl will quickly return Gecko as the first result. So whilst not a lot of time went into naming this, we're quite proud of the name, and we hope you are too. And the second of these aspects is Gecko Delete. And this is the aspect that handles CCPA compliance through redaction of encryption keys. The main focus of this talk is going to be on Gecko crawl, as this was a computationally intensive process, as we had to process all of our data. And this is what required most optimization in Spark and utilization of Delta tables.
So now we're going to dive into a little bit more of the technical details as to how Gecko crawl and Gecko delete work. So to begin with, I'm going to introduce you to our architecture diagram for Gecko crawl. And before I go into the details, I just want to point out that this diagram is split into three main sections. So the first, you see this arrow here on the left. This represents the first section where we deploy our configs. The second section I'll refer to is this bit in the middle where it says the encrypt banner over it. And this represents where we encrypt data. And then the final section is this section on the far right with the yellow strip. And this represents when we're talking about the master table. So to begin with, to go through this diagram, the first thing we do is deploy our configs on runtime. These configs contain information on which data needs encrypting and generates an encryption key for each row for each table that is being run. And the reason we do this on runtime is to ensure that we have encryption keys generated for every row, since data may have been ingested into the lake between when Gecko was last run and when it's currently running. So after we've generated these encryption keys, what we do is we thread notebooks at the source level and then at the table level. And this is to ensure ultimate parallelism. And then once we've threaded at the table level, what we do is we then encrypt the data. And we encrypt this data at 3 write locations within our ELT process. So if I point you now to these 3 little directory symbols at the bottom, raw, schema, and output, it'd be worth remembering these as the 3 write locations within our ELT process, as we'll touch on these again later in the presentation. Then finally, once encryption is complete at each of these 3 locations, we then generate something called a master PII table, which contains all personal information encrypted within the Petcare Data Platform. So the first thing that we do then is generate the encryption keys. And the way we do this is we loop through each data source and each table specified in the run, and first generate something called a salt key for each row within the table. These salt keys are simply random 16-byte binary strings, and this salt will provide the basis of forming the encryption key later. So what we actually do is we produce one salt key per source ID, and source ID is what we refer to as the ID column to base the encryption on for a given table. And here it's important to note that if the table has a client ID, we'll prioritize the client ID as the source ID rather than the primary key of the table. And this is because if we receive a CCPA request, typically that will be in the form of a client ID. So we want to ensure that if a client ID exists in the table, we want an encryption key generated for it. So here we can see an example of this table and what it looks like. So if we look at the different columns, we've got the data source. This would be the data source that's specified in the run. We've then got the ID column, which will typically be the client ID, if not the primary key. Then we've got the source ID, which is the value of that ID itself. And then we've also got the salt here as well, which is the random 16-byte binary string associated with that ID. So you may be wondering how this salt is actually used to encrypt data. Well, the salt key combined with a password is what generates the encryption key. These passwords are stored in Azure Key Vault and are actually stored completely separate from where we store these salt keys. So this table that you see here is actually stored as a Delta Lake table within our lake. And the reason we actually separate these out into two is just to add an extra layer of security. So you can imagine that in order to actually obtain the encryption key and decrypt data, you'd have to know how the process works of combining the salt and the password. And further, you'd need to have access to two different systems, the Delta Lake table and the password in Key Vault. So it really just provides an extra layer of security. So how do we actually generate this table? Firstly, what we do is we generate an incremental data frame for each table that is executed as part of the run. And this will be done through a Pythonic for loop. Then once we've got those incremental tables for each table, what we'll do is we'll union them together and aggregate to generate the final data frame to ensure that we've got a single salt per source ID. And we've optimized this process by not actually calling any actions within the for loop. And this way, because of lazy evaluation, Spark can actually iterate through that for loop really quickly and build up the execution plans required without calling any actions. Then when an action is called on write, when we actually go to deploy this config, that is when Spark can efficiently distribute this data across the cluster and process this deployment as fast as possible. We also have the added benefit here of knowing exactly which tables an ID exists in. And this is making use of PySpark's collect list function. And this is that final column that you see here in the table, tables exist. So since we're iterating through every table, we actually have that as a value within the incremental data frame. So then what we can do is when we run that aggregation or window function, we can run the collect list function, bring those tables together, and we know exactly what tables a specific ID exists in. And this can be particularly useful, again, for CCPA reasons, in case we need to know where an ID exists. So as well as utilizing Spark here by not calling any actions within this for loop, we also utilize Delta Lake features too. So for every deployment of this table, we run an optimize and a Z order on source ID, as well as partitioning the table by data source. And this way, when we then join back to this table to get the encryption keys when we're running the encryptions, we can ensure that the queries are executed much more efficiently. So after fine tuning this process, thanks to Spark and Delta Lake, we've managed to get this deployment down to roughly 10 minutes per source.
So as previously mentioned, the data encryption aspect of the Gecko crawl process is very computationally heavy. And we've had to implement some different tools which enable this process to be done more efficiently and in a reasonable time frame. The first of these is to utilize multi-threading of notebooks at the table level. And this allowed us to encrypt data in parallel and maximize the usage of Spark. We also have 3 locations which are required to encrypt due to 3 write locations in the LT process. And this is what Jason mentioned earlier with the raw, schema verified, and output locations. So this again increases the complexity that we're dealing with in the crawl process. And in terms of how the actual encryption works, the first thing we do is that when we're encrypting a table, we read it in, we then join it to the ID salt table, and this allows us to derive the salt key by using the given ID column that we have in the ID salt config. From here, we then apply a Fernet encryption PySpark UDF, and this is applied across all PII columns. The Fernet package is actually built up into the Python cryptography package, and it's a symmetric encryption mechanism. And we've actually put this into a PySpark UDF, which can be applied row by row to ensure that each row is encrypted as it should be. Once we've encrypted the data, this is then validated, and we overwrite the existing ingested data. We also have the ability to decrypt and obtain the original PII value when required and permitted. And this is actually inbuilt into the validation step. So the first part of the validation that we do is to perform counts to ensure that no data has been gained or lost when performing the encryption. And the second part is that we decrypt the data and write it out. And this ensures that all the data that we had originally can be regained and nothing is corrupted or lost. And here we have an example of some encrypted data. So on the left and right, you can see some non-PII fields, which have just been left as is. But the note column here is a PII column. And via the encryption, we now have been left with a Fernet token in place of the original data that was there. So if anyone could gain access to this table that shouldn't, this data is completely meaningless. And the only way that they could regain the value is if they had access to the passwords, the ID salt table, and also a knowledge of how the process works intrinsically. So going back to the three write locations that we have, we're actually dealing with two different types of file as well, which again adds another layer of complexity. So within the raw and schema verified locations, we're dealing with Parquet files. And here we're actually dealing with individual files for each data ingested. And we're actually required to encrypt each file path one by one. And this was up to 600 in some cases. So this meant that the encryption process was really hard to optimize as we were dealing with a huge number of individual parts. Conversely, in the output location, we were actually dealing with a Delta file format. And here this massively simplified the process as we were only dealing with a single Delta table for all dates and a single path to encrypt. And of course, the encryption process was easily optimized by Spark due to things like partitioning. So I'm going to talk you through a few issues that we came across during the optimization of the Parquet aspect. So some initial shortfalls that we had was that we were actually looping through file by file. And as I said, this could be up to around 600 files. Another issue was that data wasn't partitioned across the cluster, leading to extremely low utilization. And what we can see here on the right is a ganglia screenshot of our cluster, and we're operating at very low utilization, around 4.7% on average. The issue of partition of data was made worse by skewed data sets that meant the data wasn't partitioned well across the cluster. And this typically occurred within data sets that had free text fields. And the consequence of having such a low cluster utilization was that not only runs were extremely slow, and we were actually hitting the 48-hour Databricks notebook limit, but we're also wasting lots of cluster resource and also hence wasting lots of money. So the solution that we came up with was to implement parallelism with threading and make the use of Apache Spark features. So the first thing that we did was increase the number of partitions after shuffle, and this hence removed the skew effect and ensured that Spark was operating at maximum parallelism because we had an even distribution of data across the cluster. We then also implemented Python concurrent futures via multi-threading, and this allowed us to execute encryption logic for multiple Parquet files across multiple workers in parallel. And the consequence of this meant that we weren't waiting for tasks to finish before moving on to the next file, which massively increased the speed. And as you can see here from the ganglia screenshot on the right, we actually operated a much higher cluster utilization for the same process, with a baseline of around 60% utilization, going up even as high as 90%. And this was obviously very beneficial. As we increased the cluster utilization, this in turn reduced runtime from days to hours. We also did experiment with a number of Python workers that we were using, but we actually saw a high utilization at a lower number of workers. And this really showed that there was a balance required in order to find the most optimal configuration. But as we've reduced the runtimes by such a drastic percentage, we didn't spend too much time hyperparameter tuning.
So the third and final piece that I want to talk to you about within Gecko Crawl is the master table. So here, this is where we collect all of the PII within the Petcare Data Platform into a single Delta Lake table within our lake. And this table contains fields for each PII attribute, so name, phone number, email address, addresses, and notes. And each of these fields contains an array of encrypted data for each PII for that specific source ID. So if we have a look here at an example of the table, we haven't managed to fit all of these fields on the slide, but you can see here we've got columns for data source, table name, the ID column, and the source ID. And these are columns which can match to that ID salt table before. And then on the right-hand side, you can then see name master, address master, and we have those other columns as well. And what this is an array of every name, for example, that is associated with this ID. So you can imagine if there's fields, say for first name, last name, perhaps next of kin, first name, next of kin, last name, these will all be collected together into a single row. And the reason why we did this is because we thought that given that we were looping through all of the tables anyway, all of the PII tables, we thought it would add some business value in the future to actually collect all of the PII into one place. And the reason being is that in the future, we're hoping to create some sort of custom built in-house NLP model, which we can use for potentially PII detection in the future.
So I'm now going to talk you through the Gecko Delete process and show how this process has massively simplified our CCPA compliance. So the Gecko Delete process offers superior simplicity, consistency, and tractability. And this is extremely important for management of the process and also audit scrutiny. And the process is as follows. So a request is ingested into our configs, and this then triggers the delete pipeline. From here, the request ID is used to filter our ID salt config, and the relevant salt is redacted. And that is how simple it is. The client's PII is now irretrievable, and the non-PII structure is maintained. I'm now going to take you through a visual example of how this actually works. So on the left-hand side, we have an example request come in. So this is coming from a Mars Petcare business unit, and in this case, Banfield. So we get this ID come through, and this is ingested into OneTrust, which is the Mars-wide CCPA piece of software. Once we have this in OneTrust, we then can identify the client within our vaults. From here, we identify the client within our ID salt config, and their salt is redacted. And without the salt ID, the encryption key can no longer be generated. As Jason said earlier, it's the salt and the password which make up the encryption key. So without that salt, that user's PII data is no longer retrievable. And by only removing a single record, we've actually achieved the fact that the client's PII can never be retrieved, and also that all of the non-PII data stays exactly as it was in the lake. So if you can imagine in the middle there, that row will stay exactly as it was in the lake, but that PII is no longer retrievable. And this shows how it really is a consistent, reproducible, and tractable method.
So now I'd just like to summarize the key benefits that we have through Gecko, as well as some of the future work. So we have 5 main key benefits that we've identified. The first being data security. So as we've mentioned previously, every instance of an individual's PII is encrypted, which means that data can never be, personal data can never be just viewed on the fly like it used to be able to. The secondly, speed. When we receive a CCPA request, it's now just a single filter and redact in order to be CCPA compliant, rather than having to remove that ID in every instance that it existed. Thirdly, auditability. So we have a bespoke logging system in place, so we can keep track of where PII is being used, where it's been redacted from and where it hasn't. And this just makes things really, really easy and simple. Fourthly, automation. So this process can now be easily monitored as part of a BAU process, again, rather than having to spend a large amount of time trying to find every instance of that ID. And finally, data integrity. So by not deleting the rows, the data structure and the integrity is maintained. So finally, just to wrap up, some points around the work that we've got left with Gecko. So firstly, we'd like to build a future custom NLP model to use for auto PII detection on ingestion. We'd also like to create an API layer over key access in order to enhance speed and security. And finally, we'd like to integrate the Gecko module within the ingestion process itself. So rather than having 2 end-to-end processes, one for the ELT pipeline and one for Gecko, we just use Gecko as a module that is called within the ELT pipeline itself, again, to enhance speed. Thank you for listening, and we look forward to hearing any questions you may have.